So for radiation, we're going to use the Stefan-Boltzmann law. And here it is written out. So the total radiant energy is proportional to, first of all, the surface, the emissivity of the surface. So that depends on whether the surface is a matte black finish or a shiny silvery finish. Those change the way that body radiates and absorbs energy. So the emissivity of the surface. The Stefan-Boltzmann constant, that's our proportionality constant. It's also proportional to T to the fourth power. So anything, that's sort of a black body radiation law. When something gives off energy, the energy it gives off is proportional to T to the fourth, and temperature has to be in Kelvin. And of course, it's proportional to the surface area. If a body is radiating energy, you'd expect it to be proportional to the surface area. And then the energy radiated is proportional to time. So usually what we do is we divide both sides by time, and we talk about the power radiated. But we have a time in there. Okay, so we're going to use this equation in looking at our problem with the wood-burning stove. And in the first part, the stove is unheated. So it's at the room temperature. And what we're going to look at is the net power radiated by the stove. So first thing we're going to do is look about the power that the stove emits. And then we're going to look at the power that it absorbs. So power is energy over time. And like I just said, if we take the Stefan-Boltzmann law and we divide both sides by T, what we end up with is emissivity, the Stefan-Boltzmann constant, T to the fourth power, and the surface area. And all of those things are given. The temperature, we have to put that into Kelvin. And the surface area was given 3.5. And we plug all those things in and we get joules per second, which is a unit of power. We call those watts. Capital W for watt. So 1,280 watts. And we sort of have to know now that the stove's not changing in temperature. They tell us it remains at a constant temperature. So that means that the power that it emits is equal to the power that it absorbs. And the power absorbed is going to be 1280. And we end up with our net power is the power emitted minus the power absorbed. Zero watts. And basically we know that's true because we're not doing anything to the stove. It's in an equilibrium state, and it's just going to stay in that state. So the power emitted and the power absorbed are the same. Now let's take a look at the case when we've got a fire going, when that stove is heated up. So first of all, the power emitted. Q over T emissivity, Stefan-Boltzmann constant, T to the 4th power, and the surface area. We know these things. 5.67 times 10 to the minus 8 is our constant. We have to convert our temperature into Kelvin, so we have 471 Kelvin to the 4th power and 3.5 square meters. And this answer better be more than we got when it was cold, right? Because we expect it to radiate a lot more energy when it's hot, and it does. It's 8,790 watts, which is much more energy radiated than when it's cold. Now let's look at power absorbed. And this is where a lot of students get stuck. They say, okay, the stove is hot. I can use the Stefan-Boltzmann law and figure out 8,790 watts being radiated. But they forget that even though the stove is much, much hotter than the room, it's still absorbing energy from the room. So let's take a look at how much is absorbed. The energy absorbed by the stove when the room is 29 degrees C is the same as if the stove was emitting energy in a 29 degree C room. In part A, we saw that the power emitted by the stove at 18 degrees C was the same as the power absorbed by the stove at 18 degrees C. We reasoned it out, I guess. And so now the room is 29 degrees C. So how much power is absorbed by the stove when the room is 29 degrees C? Well, the same as it would emit if it was 29. So that's going to be equal to the emissivity times the Boltzmann constant times T to the 4th times the area. And I've got 0.9, 5.67 times 10 to the negative 8th. And now it's 302 Kelvin to the 4th power. That's from the 29 degrees C room. And 3.5 square meters. And so I got 1,490 watts. So the power absorbed by the stove when the room is 29 degrees C is the same as the power emitted by a 29 degrees C stove. And we're now interested in the net power. And so it's the power emitted minus the power absorbed. 8790 minus 1490. Those are watts. And I've got 7,300 watts. So the key in this problem, I think a lot of people can get through the first part okay, and the first half of the second part, and the tricky part is just getting the fact that even though that stove is much hotter than the room, it's still absorbing energy from the room. Much, much less than it's giving off, but it's still absorbing some energy.